All right, so put into your calculator, into your x for line 1 and your y for line 2. Okay, so your slope should be about 4.13 times 10 to the negative 15 eV times seconds, and your y-intercept is negative 2.12 eV. So what I did, I want you to look at the graph that I scanned, printed for you. And we are going to, goodness sakes. So let's Okay, so this is a graph, and I just want us to make our line of best fit on this and kind of talk about it a little bit and try and just reason our way to discussing this a little bit before we jump right into all the rest of our calculations. So I'd like you to use a ruler, at least the flat edge. If I put a ruler on my thing, I can't draw a line, it won't work if it's touching. Well, I guess I could maybe try it like this. I hold it above. Haha.
So what you get is your slope and stuff.
My slope should be like 4.15 times 10 to the negative 15. Or 4.13, something around that. Okay, well that's fine. Okay, so let's just look at our slope and our y-intercept and x-intercept and kind of reason what's going on here. So, and I'm actually going to continue this down to the bottom. I'm going to kind of extrapolate. Okay, as well. Okay, so let's think about this for a second. If this is our frequency and this is our kinetic energy, here, okay, where it is at the x-intercept, okay, so this would be like our x-intercept, this is where our EK is 0, right? Like just logically looking at that. So this frequency, okay, the frequency when EK is equal to 0 is then the threshold frequency. Right? Because if that's the frequency where, say, that we need to make it more than that in order to have energy of electrons, then that's how we find our threshold. Okay? So if you're looking at your graph and you're trying to determine, it says ask about threshold frequency, and it's kinetic energy versus frequency, look at your x-intercept. Okay? And then your y-intercept is when your frequency is equal to 0. So this is the amount of energy really required when your frequency, if like your frequency is at its minimum place. So when we think about this, okay, this is like the work function. Because work is a function, really means how much energy is required. So that y-intercept is work function. And actually it's going to be negative work function because it's below the graph. And you'll see in our formula that it's negative work function. So there's going to be a question in your assignment where you're dealing with this type of graph, and it's going to be a little bit different, okay? Where there's going to be just one extra layer to it, but don't get too overwhelmed. Just if you think about some things logically, I think you will be able to figure out that question. So now let's go back here and write out our physics formula and equate it to our graph, what's happening in our graph, right? Because when we are trying to interpret things with our graph, we start with our original physics formula, and then we manipulate it to look like y equals mx plus b. So what's happening here, we assume things with our law of conservation of energy. So our E incident is equal to our EK max plus W. My EK, or just EK of my electrons, is my Y variable. Okay, it's my Y axis. So I want to get this so that it kind of looks like my Y equals. So I'm going to leave it on this side and bring the W over here. So En minus W is equal to Ek. Now my my manipulated variable is the frequency of the incoming light. So I need this to include frequency because that's what I'm manipulating is my incoming light. So I'm going to go, this is H times F minus W is equal to Ek. And let's just write it the other way so that we can have some consistency. So now our F is our X value. So if this is Y is equal to M, so then my H is my M, times X, which is F, minus W. This is my B. My y-intercept. Okay, so now we have our physics formula to work with. So it says, for B, it says, what is the significance or the meaning of slope? Well, what is slope here? What variable is it? What is H? Planck's constant. Okay, that's really, really important. Because this is kind of how Planck's constant was developed, is because the slope of every line that was done for these experiments was the same. Regardless of the metal, regardless of the light, every slope was constant. So now for your question that you had about in your assignment, Hayden, that you had about number 17, I think it was. no, if 12, you would show, okay, that every slope should be Planck's constant, which is EK over F. Like using, if you used a graph that was EK versus F, every slope should be Planck's constant. So that's, 12 is wanting you to identify Planck's constant, really, is what it's trying to get at. So for this one, we know for B, for our answer for B, it's definitely got to be, it's about, this is H, which is Planck's constant. And what was our slope that we found out? You got like about 4 point whatever you had. I got 4.13 times 10 to the negative 15 eV times seconds. Okay, so that should be, you know, close to, that makes sense because it's close to our actual Planck's constant, which is 4.14 times 10 to the negative 15 eV times seconds. Okay, so every slope of these types of graphs should be about the same. Now it says, use your graph to determine the work function of the metal surface. Well, work function is our y-intercept. Negative work function is y-intercept. So we can say C, our B is equal to negative W. Our y-intercept is negative W. So we're looking for work function. So therefore W is equal to negative of B. Well, my B was negative 2.12036, etc., eV. So then my W, my work function, is 2.12 eV.